Welcome to a video lesson on Infinite Series. And if you haven't watched the unit intro video, I recommend watching that first before you watch this lesson. It'll help you understand why we would study some of the concepts in this unit, which for some CalcBC courses is the last unit of study in the course. Otherwise it would be parametric, vector, and polar. Now what you have in front of you is a capital sigma, a Greek letter, which in math practice represents the sum of numbers or the sum of terms. And when we have an infinity symbol above the Greek symbol, that means we're dealing with an infinite series. So in this lesson we're going to talk about that infinite series, a specific type of infinite series called a geometric series, and talk a little bit about how that applies to infinite repeating decimals. So first thing, an infinite series is basically a sum of terms, and in this case we'll use little a's. So a1 plus a2 plus a3 plus all the way up to a sub n, which it's assumed that n is basically an infinite number or a very large number. And this entire sum could be written succinctly with the sigma notation, like so. So this is basically read the sum of the series a sub n, or the series a, starting at n equals 1, going all the way up to infinity. Many times infinite series will stay away from the notation that starts with the index n equals 0, because sometimes that 0 will cause the series to be undefined, something raised to a power or a division going on. So that's it. That's the definition of an infinite series, a sum of terms that go all the way up to infinity. Now a partial sum is really just what it says. It's a sum of part of the series. It's the sum of the first k terms, or d terms, or l terms, whatever letter we want to use to represent the number of terms we're going to add up. So again, it's just the sum of the first k terms. And we don't use n because n is a number that is allowing us to go up to infinity. In a way, we're saying that this series is finite, such that n is a number, but we're letting n approach infinity. Here are a few examples. We're basically trying to decide if these series diverge or converge. So with the first one, we have the number 2 being subtracted and added to itself until infinity. So if you notice, the first term is 2, and then the second one is negative 2, and positive 2, and so on. So the partial sums of this particular series changes as time goes by, or as the number of terms increase. So what we could do is we could find the partial sums of this particular series. So let's just talk through that. Well, the first term is just 2. That's the sum of the first term. The sum of the first 2 terms is 2 minus 2, which is 0. And then the next term, so we have 3 terms, 2 minus 2 plus 2. Well, that's pretty simple. That's back at 2. And then 0, and 2, and 0, and so on, forever. So the limit, as the number of terms goes to infinity of that series, or sum, well, that's undefined. It's either 2 or 0, right? Well, I guess I should say does not exist at this point. We got some calculus knowledge. And so if the limit does not exist, then that means that's a divergent series. The divergent series, how about that? And if we're trying to find the sum of this particular series, well, we really can't. So the main idea of this particular example is that this particular series diverges. Let's take a look at the next one. So we have 7/10 plus 7/100 and so on, all the way up to n terms. Notice that the n would start at 1, 10 to the 1. So let's add up the first term. The first term is 7/10. And what's 7/10 plus 7/100? Well, I'm going to rewrite this as a decimal. I'm going to say this is 0.7. So the next one is 0.77. 0.777. Finally, the fourth partial sum is the sum of the first 4 terms, which is 0.7777. How lucky. So now what is the limit of, not the sum, and I didn't really talk about that in the last example, but what is the limit of this series, meaning what is the nth term. That's what this is asking for right here, this limit. And so when I think about this 7 over 1,000, it's 7 over 10,000, 100,000, 1 million, 1 billion. That means the limit of the nth term is 0. And when the nth term approaches 0, that means that the actual series converges to one number. It means the terms are getting so much smaller that you could actually add them up, all of the terms, and they'll approach one sum. And I'm proposing that the sum of that would be 7/9. You might think the sum is 7/10 at first, right? Because the first term is 7/10 and each thing is getting smaller, but obviously it can't be 7/10 because we're adding something to 7/10. So the second one is converge. That's the main idea. And this first infinite series is called an alternating series. That means the sign changes. You don't need to know that right now. And then the second series is a geometric series. So let's talk about that a little bit more, starting with the general form. Well, here it is. So the first term in a geometric series, we'll call it A. And that means the second term is A times R, which is something that we learned in sequences. And so basically that's A times R to the 1. And then each power gets larger and larger. Now, because n minus 1 could be a 7 or a 9 or even a 4, there are these ellipses here to show that there could be terms in between there. But this is the key, the Riemann sum from 1 to infinity of that expression. So a few more things to note here, that A is always the first term and R is called the common ratio. So if the ratio between the terms changes, then we don't have a geometric series. It's not the same ratio that's happening. And something special, if the common ratio acts a certain way, then we have convergence. And that's this. It's pretty cool. If the absolute value of R is less than 1, so a fraction in between 0 and 1, doesn't matter if it's positive or negative, the sum actually converges, the series converges to A over 1 minus R. The first term divided by the difference between 1 and R. Now, if R is greater than 1, that means all the terms are getting bigger. And we have divergence, which we don't really like. We can't really do much with that. Our experience ends with that situation. And it doesn't matter if R is, so let's say R is negative 1/2. That means the terms are bouncing between negative and positive, but they're getting smaller. And then if we have R is positive 1/2, they're just getting smaller. But if they're 3/2, then the terms are getting bigger, diverging, adding bigger numbers, and we don't know what happens. All right, let's take a look at a few examples. Here's the first one, the Riemann sum from 1 to infinity of 5 times 1/2 to the n minus 1. So I just mentioned, the fact that R is 1/2. So in this case, I'm just going to write down what I know. A is equal to 5, and R is equal to 1/2. So already I know that this is going to converge because the absolute value of R is less than 1. So in this case, what we're doing is we're basically trying to find the sum of this series. So that sum is 5 divided by 1 minus 1/2. Hey, that's kind of cool. It's kind of neat that we could add an infinite number of terms, and we would get the number 10. That is the actual sum of an infinite number of terms. Many mathematicians thought about this in the past few centuries and thought, wow, I wonder how we could extend this idea of how numbers act to how maybe polynomials can act and what we could use with that sort of information and how powerful that could be with technology. Well, we're not there yet, so don't worry. Okay, I mean as far as our work together as a class. All right, the second example is very similar. We still start with 5, but I'm using a k here just to show you that we could change this letter. It really doesn't matter. We still have an infinite series, and we have the number 3/5 as the R. So I'll just write that down again. A is equal to 5, R is equal to 3/5. And so knowing in my brain that 3/5 is smaller than 1, the sum is 5 over 1 minus 3/5. And that's 5 over 2/5, which is 25 over 2. Well, I think I actually meant that to be a 1 right here, because when you don't see a number listed in front of an expression with the power, then we're assuming that first term to be a 1. So if you see that, notice that. Well, I have two final thoughts here, and one of them is just basically thinking about this series and basically what these terms look like. We have the first term is 5, and the second term is 5 times 3/5. The third term is 5 times 3/5 squared, and so on. So I just want you to see how these numbers are decreasing. We have a 5, and then we have a 3, and then this is 3/5 squared, so there's a 25 in the denominator. One of them divides out with this 5, so we have 9 over 5, and so that 9/5 is less than this 3 over here. 9/5 is 1 4/5. So these numbers are decreasing, and we know that for two reasons. First, we could actually do it, and second, we know that 3/5 is smaller than 1. Okay, finally, the last thing is this. Thinking about what does 0.33333 and so on mean, I want you to see that you could write this as a sum of terms, that this is 3/10 plus 3/100 and so on. And one of our goals, one of our challenges is try to figure out how to write a specific number or a specific expression using individual terms and a general term, something like 3 over 10 to the n. And that's it, but just thinking about how, when we press a math enter on our calculator is taking this decimal and turning it into a fraction, and in a way it's using an algorithm like this, and it's saying that a is equal to 3/10 and r is equal to 1/10. Not 3/10 again, be careful. So it could use that information to find out the sum as a fraction, which is kind of cool. And so we'll talk about more of the type of things that your calculator will use based on these concepts. Hey, thanks so much for watching. I hope you'll start to appreciate the beauty of what we will be studying, and it will work out quite nicely for you. Thanks.